good. Thank you for the light. All right, so let's get started. I thought of a better way to do the cohomology with compact support of the Meyer-Vittor sequence of the open Möbius strip. So I want to redo that, but in order to save time, I've just put down on the board like what we already did last time. Okay, so we covered the Meyer-Vittor, we covered the open Möbius strip with two open sets, U and V, like this. And the intersection of U and V consists of two components, A and B, okay? And so we've got these four open sets, U, V, A, B, which are all open rectangles. And they are diffeomorphic to R2. Okay? So we know their cohomology with compact support. And then we write down the Meyer-Vittor sequence. Okay. Now, okay, so let me see. So, okay, so here is the Meyer-Vittor sequence with compact support. And we already know H0, right? We know H0 of any manifold, so we can disregard that. And in H1, R2 has a cohomology with compact support 0. And then we have H1 of the Möbius strip with compact support, which we don't know. And then in H2, we have R plus R and R plus R, these two terms. And the crucial map to figure out is this J star, okay? And that's what I want to discuss today, a better way than last time. Okay, so a generator of H2, right, is a two form with compact support. And the identification of H2 of R2 with compact support with R is given by integration. Now, in order to integrate, you need an orientation. Okay? Now, if we have R2, then there's this standard orientation, which is counterclockwise. But here, we just have open sets, UVAB, that are diffeomorphic to R2. Okay? So in order to have this identification of H2 with R, you first have to orient all of your open sets, okay? And you can orient them any way you like, because all you need is to have an identification of H2C with R2, okay? Yeah, so, I can orient them any way I like. Let's say, okay, now here U is connected, but in the picture, it has two rectangles, because this edge here on the left is supposed to be identified with this edge here, in this particular way. Now you can orient this part of U arbitrarily. But then here, then it's not arbitrary because it has to be consistent with this. Okay? And so you see that if you put this piece over here, in order to have a consistent orientation, it has to be like this. Okay? So the arrow has to agree with the arrow on this edge. So therefore, over here, in order for the orientation to be consistent, it has to go like this. Okay? these two arrows have to go in the same way, like here. So this is the only part where it's not arbitrary. Okay, now once you have orientations on all the open sets, then you can choose generators of H2C, okay? And so these would just be two forms with compact support that integrate to one on each of the open sets, okay? And so we call them, let's say, we just choose them. So, and okay, so I'm gonna call omega u a two form with compact support. Omega u, a two form with compact support on u, such that its integral over u is 1. Okay? It will give a generator of H2C of u. And then similarly, for the other open set, so omega v, omega a, omega b. Okay? And now we have to figure out what this J upper star is. Okay? Now, this is with compact, sorry. This is with compact support, so it should be J lower star and I lower star, okay? Yeah. And the definition of J lower star of, homology class is this, J lower star. Do you remember what J lower star is with compact support? You have the intersection included in U and in V. Pardon? Yeah, it's a sign inclusion. So J lower star, it is minus J U lower star of omega, and then J V lower star of omega, okay? So this is the inclusion of the form, into U, like, okay, so omega, let's say, is in H2C of the intersection, and J lower star is the signed inclusion. I mean, I should put the, take the cohomology class of the whole thing. Yeah. Okay, and now here we have two generators, omega A and omega B. Okay, yeah. So we should try to figure out what J U lower star of omega A is. Okay, so this is omega A is the form with compact support on A that integrates to 1. Okay, so its support is in A. By extension, yeah. So, you can also view it as a form on U by extension by 0. And to figure out like which real number it goes to, you just have to integrate, okay? Because that's how you make the identification. So to figure this out, you you need to integrate omega A on U, okay? If you get 1, then it would be the generator of the cohomology of U. But let's see what you get. If you get 3, it would be 3 times the cohomology, 3 times the generator, omega U. So because the support of omega A is in A, when you integrate over U, it's the same as integrating over A. Okay, so support of omega A is in A. So outside of A, the integral contributes 0. And this, by definition, is 1 because, let me see. Yeah, because A is this part here, and it's oriented the same way. Okay? So you get 1. Okay? And therefore, omega A will just go to the generator, omega U. Okay? Okay, and then what about JV star of omega A? Okay. Now let's see. So A is also in V, and so A is here, and it's oriented the same way. So you also get 1. Okay, so I will just say similarly. When you include it in V, you get the generator. And then what about JV star of omega B? Tell me what you get there. So I have a generator. I have a 2 form here that integrates to 1. I extend it by 0, and I integrate it over V. What do I get? 1. Yeah, because the orientations are the same. So, okay. All right, and then one last one is JU star of omega B. Okay. Yeah. Okay, so you have to integrate omega B over U. And this is the same as omega B. Well, is it the same as omega B over B? Well, the thing is like B is included here. Okay? But B is oriented counterclockwise, and this part of U is oriented clockwise. So they have opposite orientation, and therefore there is a minus sign. Okay? Because U and B have opposite orientations. Yeah. Have opposite. And that's why you get a minus sign. So this integral will be -1. And therefore, when you extend by 0 omega B to U, it doesn't go to the generator, but it goes to the negative of the generator. Okay? Yeah. So that is the only part that is a little bit tricky. Okay. All right, and so now we can figure out what J star is. Okay, so um, okay, so yeah, let's write down J star. Okay, so J star of omega A will be the sign inclusion minus JU star omega A, and then JV star omega A. And so that would be minus omega U and then omega V. Okay. And then um, probably I should move it up. And okay. And then J lower star of omega B is minus JU lower star of omega B, JV lower star of omega B, and then this is minus omega U and omega V. So it is omega U, omega V. Okay? Now, in terms of real numbers, then J lower star, omega A, it's a generator in the first component. Okay, so it's 1 there. And then it's 0 in the second component. So 1, 0 will go to minus 1, 0, minus 1, 1. Okay? Omega V is 1. And then J lower star of 0, 1 will go to 1, 1. Okay? And this matrix, okay, has non-zero determinant. Well, you see these two vectors are linearly independent. And so that means J lower star has rank 2, and so it's an isomorphism. And once you know that it's an isomorphism, then the rest is easy. Okay. So let me see. This goes up, and this goes down. So let's call this map D star. Okay. Okay, so we have H1C of M, okay? Because D star is an injection, so H1C of M is the same as the image of D star. And that's equal to the kernel of J star, and J star is an isomorphism, so it's 0. And then H2C of M, okay? So H2C of M, because this is surjective, it's the image of I star. Huh? Yeah. And by the first isomorphism theorem, that is the domain R2 over the kernel of I star. And the kernel of I star is the image of J star, which is R2, because J star is an isomorphism. So you also get 0, okay? And so the cohomology with compact support of the open Möbius strip is 0 in every dimension. Now, in the homework, I ask you to do this calculation, but I put different orientations on U, V, A, and B, you know. So the map J star will be different from this one. And basically, that's what you have to figure out, okay? Yeah. Oh, by the way, I have also postponed the deadline for the homework from Thursday to Friday, okay? Because although I want to discuss Poincare duality today, it's aspirational, you know. I may not get to the end of it. And there's one homework problem about Poincare duality. Yeah, yeah. So we'll probably finish Poincare duality on Thursday, and then you can do your homework and you can hand it in on Friday. Okay, okay, very good. Already spent 25 minutes on this. Yes, good. Oh, okay. So I'm not looking at the compact Möbius strip. I'm looking at the open Möbius strip. Okay, and that means that's why I kind of erased part of the boundary. So you know, it's not a compact set because it doesn't include the boundary. Yeah. Right. Yeah. If I had included the boundary, then it would be a compact set. And then you're right. Then the cohomology with compact support would be the same as the usual cohomology. Okay. If you include the boundary, right, then this, you know, like this wouldn't be diffeomorphic to R2. Because you don't include the boundary, right? You can just expand it to infinity, you know. So it would be diffeomorphic to R2. Yeah. Yeah. If you had a boundary, then yeah. Yeah, it's not diffeomorphic to R2, then you can write down, you know, the Maya-Vittoris sequence. Yeah, very good question. Thank you. Okay, so, well, you know, the cohomology, just the ordinary cohomology of, you know, a surface, say, might be infinite dimensional, right? Can you think of an example? Like, what would be a surface whose H1 is infinite dimensional? Okay, now in the homework, you did the cohomology of a multiply punctured plane, right? If you take out 3 points, what is H1 of R2 minus 3 points? It would be R3, yeah. Yeah, and if you take out 5 points, H1 is R5. So if you take out infinitely many points, let's say you take out, all the integer points on the real line, then the cohomology would be infinite, right? H1 would be infinite, yeah. Now, we usually like the cohomology to be finite dimensional because then the dimension would be a numerical diffeomorphism invariant, okay? And so there's a theorem that guarantees that you have finite dimensional cohomology, okay? And that's what we want to discuss, okay? When does the cohomology of, when is the cohomology of a manifold finite dimensional? And the way I will prove this theorem, is to use the Maya-Vittora sequence in a special way. And it's actually a general method that you can use to prove many different theorems. We'll use the same method to prove Poincare duality and the Kunith formula and the Thom isomorphism, So yeah, it's an important technique. So first, let me define the notion of a good cover. So when is an open cover good? An open cover is good if all the open sets are diffeomorphic to Rn, and all the finite intersections are also diffeomorphic to Rn. An open cover of an M manifold, M, is good if all open sets U alpha, let's call this U, and their finite intersections are diffeomorphic to Rn. Okay? So an example of a good cover is the cover we just wrote down for the open Möbius strip. All the open sets and their pairwise intersection there are diffeomorphic to Rn. And there's a theorem that says that every manifold has a good cover. Yeah. Okay, and now in this course, I'm only working with C infinity manifold. So when I say a manifold, I mean a C infinity manifold, all right? I mean, if you want to talk about diffeomorphisms, then of course, you have to have a C infinity structure. And this is really a theorem from Riemannian geometry. And the idea is that on any manifold, you can put an inner product on each tangent space, at each point. That's called a Riemannian metric. And once you have a Riemannian metric, you can talk about geodesics. And then you can define what is meant by geodesically convex. So it just means between any 2 points, there's a geodesic. So it's a generalization of a convex set, in Rn. And then you can take an open cover whose open sets are geodesically convex will be a good cover. Okay? So that's from differential geometry. And yeah, so I mean, we're just going to assume the theorem. Okay, so I'll just say that an open cover consisting of geodesically convex open sets is a good cover. Okay, the thing about convexity is that if you have two convex sets, then the intersection is also convex, and yeah, so that would kind of guarantee that all the finite intersections, would be geodesically convex, and those sets are diffeomorphic to Rn. Okay, so we'll assume the theorem. Now, of course, every, oh yeah, right. And then then we say that a manifold is a finite type if it has a finite good cover. Okay. And most of our theorems will be for manifolds of finite type. Okay, a very large class of manifolds is a finite, are of finite type. What are they? Yeah, compact manifolds, right? Because if you have a good cover and it's compact, then there's a finite subcover, and it's also good. Okay, so being a finite type generalizes compactness. Rn is not compact, but it is a finite type. Okay? And then the theorem is that the cohomology of a manifold of finite type is finite dimensional. if okay? Um, and the way we're going to prove this is by induction on the number of open sets in a good cover. Uh-huh. So you see that if you start with just one open set in a good cover, that's Rn, and we already know the cohomology of Rn, you know, it's the same as the cohomology of a point, and that's finite dimensional, okay? Okay, and then in order for the induction to work, so we need this lemma that if you have open sets U, V, and U intersection V in a manifold, and they have finite dimensional cohomology, then the cohomology of the union is also finite dimensional. Okay? Yeah. Uh-huh. And the proof is to apply the Miyavi-Torres sequence to U and V. So in the Miyavi-Torres sequence, you have HK of U plus HK of V going to HK of the intersection. Right, that's a difference. And then you have the restriction HK of the O union. And HK of the union comes from HK minus 1 of the intersection. Right? And this one is the restriction, and this one is the difference. All right. All right. And so let me see. So we know that this is finite dimensional. And we know that both of these are finite dimensional. Okay, and so we want to conclude that the union is finite dimensional. let's see. This should be quite easy. No, HK of U union V. Yeah, so I want to relate it to these two other terms. And by the first isomorphism theorem, I know that this over the kernel of I star is the image of I star. Right? And so let's see. And the kernel of I star is the image of D star. Yeah. Okay, so first of all, now this implies that as vector spaces, this is isomorphic to the kernel of I star, direct sum, the image of I star. All right, because vector spaces are determined completely by its dimension. And then the kernel of I star, yeah, so over here, that's the first isomorphism theorem. Okay, and then this is kernel of I star is the image of D star. Okay. Now the image of I star is a subspace of a finite dimensional vector space. Okay, so it's finite dimensional. Let me see. I guess I have to move this up and this down. Okay. So the image of D star, where is it? Over there. Yeah, so the image of D star, that's a quotient. Is a quotient of H K minus 1 U intersection V. And so it's finite dimensional. And the kernel of I star is a subspace of HK U plus HKV. And so that's also finite dimensional. Okay? And so therefore the union is finite dimensional. All right. and now let's prove that a manifold of finite type has finite dimensional cohomology. Okay? And since it has finite type, we can assume that it has R open sets in a good cover. So prove a theorem. Okay. Suppose M has a good cover U1 to UR. Okay. And for R equal to 1, we know that the cohomology is finite dimensional. And so now we're going to prove by induction. So assume that any manifold with good cover with R minus 1 open sets has finite dimensional cohomology. Okay. And then, so then you let U be the union of U1 to UR minus 1, and you let V be the last open set. Okay. And then the intersection what is the intersection? So the intersection, okay, U intersection V is U1 union U R minus 1 intersect V. And so it is U1 intersect UR union by the distributive property of intersection over union. Okay, and these are all diffeomorphic to Rn. Okay, so this is a good cover with n minus 1 open sets. Thus, the intersection has a good cover with R minus 1 open sets. So in this situation, U, V, and the intersection all have good covers with at most R minus 1 open sets. And then by the lemma M, which is the union of U and V, has finite dimensional cohomology. Okay, because, oh, yeah. So first of all, let me say, so that, yeah, UV and the intersection all have finite dimensional cohomology. So that's by induction hypothesis. And so by the lemma, so does M. All right, so that proves that any manifold with a finite good cover has finite dimensional cohomology. Okay, let's take a break for 10 minutes. Come back at 11:23. and we will do Poincare duality. Okay. All right, so on the blackboard, I have written down 4 spaces, okay? And let's fill in their cohomology, okay? So who wants to do HK? Yeah, let's have one person do each one of them, all right? Yeah, so, yeah, oh, the earlier ones are easier, yeah. So tell me your name and then tell me what this column is, okay? Come on, raise your hand. Okay, if you don't raise your hand, I think I'll call you. Yi Teng. Yeah. Oh, yeah, right. HK of Rn, the cohomology. Yeah. Hmm? Pardon? Oh, H0 is R. Okay, yeah. Okay, and everything else is 0, right? Because it's homotopic to a point, right? Yeah. And with compact support, then how about volunteers? All right. Song Yun are, yeah, 0 otherwise. Okay. Okay. For the sphere, what's the cohomology of the sphere? Yeah. Okay, good. Yeah. Okay. And because SN is compact, cohomology with compact support is going to be the same. And then for the torus, yeah, let's have a volunteer. Guo Ting Ting. Yeah, dimension 1, so it's R. Oh, okay. How about, come on, somebody volunteer. Yeah. How about Du Ying Qian? What's H1? Okay. What is your name? Yeah. R direct sum R, yeah, for H1. Yeah. And H2, R, good. Yeah. Yeah. Well, you know, it's cohomology is dual to homology. And so like H1, you know, would be like these 2 circles. And H2 is the whole torus, and H0 is a point. You know, that's in homology. Yeah, it's easier to visualize in homology. Okay, the Möbius strip, that's a homework problem. But, you know, we just did the cohomology with compact support. And so we know that this is 0, 0, 0. And then what is the ordinary cohomology of the Möbius strip? And again, this is an open Möbius strip. So let me take off points on the boundary. What's the cohomology? What is it homotopy equivalent to? S1, yeah, because like you have a circle here, a center circle. And you know, you can just deformation retract to the center circle. And so it is homotopy equivalent to the circle, and the cohomology of the circle you know already. So tell me what these three things are. Yeah. Right. Okay. Yeah. Now, if you look at these examples, well, you see that this has an upside down symmetry. So does this. Okay. Now, Rn doesn't, but it has an upside down symmetry if you compare it with cohomology with compact support. Okay. So these three, so what you see is that, okay, let's write it here. The cohomology and the cohomology with compact support of Rn, Sn, and the torus, they have upside down symmetry. Okay. If you turn one column upside down, you get the other column. But it's not true for the open Möbius strip. What is the difference between the first three manifolds and the open Möbius strip? Yeah, the first three are orientable, and the open Möbius strip is not. Okay, yeah. So that's the difference. Yeah. So you have this duality for oriented manifolds, and that's called Poincare duality. And I want to explain that. And to explain that, and we, you know, we need to give a proof. Yeah. So, so let's see. Yeah. Yeah. So the reason for an oriented manifold, you have this upside down symmetry is that there is a pairing on an oriented manifold. Now, a pairing is just a bilinear map. So I can take a form and pair it with a form with compact support in the complementary dimension. Okay, so on an oriented M of dimension n, and get R okay? So n is the dimension of M. By taking a form omega and then a complementary form tau, and then I wedge them together, that will give me an N form with compact support. And because M is oriented, I can integrate. And that will be a real number. So I have this pairing. Okay. And then what we want to show is that, well, yeah, this pairing is going to give us, this isomorphism between cohomology and the cohomology with compact support in the complementary dimension. Okay? And so I'm going to just review some linear algebra. So a pairing of two vector spaces is just a bilinear map. That means it's linear in each argument. And then it's non-degenerate if non-degenerate if, let me see. So okay, if whenever you have, let's see, so if yeah, like if phi of VW is equal to 0 for all W, then that implies that V is 0. Okay? And you can do it the other way too. If phi, if phi of VW is 0 for all V in V, then that implies that W is 0. Okay? Okay, now there's another way to talk about non-degeneracy. So, a pairing B induces a linear map, let's say phi L, so a left map. Okay, so the left map goes from the left vector space V to the dual of W by phi L of V is the pairing with V, So this is a linear map on W. You put in a W here, you get a real number. Okay? And then, and so you can, and it also induces a right map. So this is the left map. And then there's also a right map from W to V dual. So phi R of W is phi of blank W. And then you can say that it's non-degenerate if these two maps are injective, right? The first condition says this. Yeah. So if this map is 0, then V is 0. Um, so phi L is injective. Yeah. Okay. So let me see. Yeah. Okay. Um, Phi is non-degenerate if and only if the left map and the right map are injective. Okay. So by the way, in case you're not familiar with the notation, so V with a little check mark is the dual of V. And the definition of that is that it's all linear maps from V to R. Okay? And then if you have a map, say F from V to W, then there's an induced map, F check or F dual, from W dual to V dual. So what is that induced map? You have to take a linear map on W to a linear map on V, right? So suppose you have a linear map alpha on W. Okay, what is the dual of F applied to alpha? Yeah, it's just composition. It's just composition. It's just alpha composed with F. Okay, so that's the dual map. Okay, and then we have this theorem that a pairing is non-degenerate. Well, we know that a pairing is non-degenerate if and only if these two maps are injective. Now, if W is finite dimensional, then you can say more. Then a pairing is non-degenerate if and only if the left map is an isomorphism. Okay, so let's prove this. So like, let's see, in this direction, so let's say phi is non-degenerate. That implies that the left map is injective. And so the dimension of V is less than or equal to the dimension of W dual because it's finite dimensional. It has a dimension, and the dimension of the dual is the same as the dimension of the space. Okay. But non-degeneracy also implies that the right map is injective. Okay. Okay, now this says that dimension of V is finite dimensional, and this implies that the dimension of W is less than or equal to the dimension of V dual. That's the dimension of V. And the dimension of V is less than or equal to the dimension of W. So the two dimensions are equal. And if you have an injective map of vector spaces of the same dimension, then that's an isomorphism. Okay. Okay. So and since the left map is injective and the two spaces have the same dimension, VL is an isomorphism. Okay, now the other direction is the same. Well, not the same, but it's equally easy. So let's not do that. And let me see. All right, so I think I'm going to stop here today. And then we will prove Poincare duality on Thursday. You should be able to do all your homework now, maybe except for the problem on Poincare duality. Okay, and that one you can do after the Thursday class. Okay. Okay.